This is question 3 from the 2008 Mmpc round 2. Prove the following inequality. So I've got some product of 1004 different fractions that are of the form n divided by n plus 1. So I've got all the odd numbers on the top and all the even numbers on the bottom. So I want to multiply all these together and show that it is bigger than 1 over 2009, but smaller than 1 over 40. So I'll consider this at first as 2 separate problems, and the first one is a little bit easier. So if we're just looking at this inequality, I think that, one thing I noticed right away, I've got a product of terms on the top, but one of those terms is a 1, which doesn't really do anyone any good. 1 times anything is the same. So what I'm going to do is multiply this inequality by 2009 on both sides. And then I'll rearrange the order of the terms. In the top, I'll just slide everything to the right by 1, and I won't write the 1. So 3 times 5 times 7 times 9, and so on, times 2007 times 2009 now, divided by 2 times 4 times 8 times 10. And the last 2 terms are 2007, 2006, and 2009 over 2008. Now when you look at this, you probably feel like there's not much to prove, right? This is a product of numbers, and each number is bigger than 1, so I'll just write that down. And I think that's enough to say to prove the first inequality. All right, the second inequality is quite a bit harder, and I'll confess before we get started that I don't think I have a 10-point solution, but I've got a few ideas to share, and if you have any better ideas, drop me a line in the comment section below, or to my face. Okay, so if you try to do the same trick that worked on the left-hand inequality, we would think about multiplying both sides by 40 and see if some kind of relatively simple arithmetic would do the trick for us. So if I multiply by 40, I can just start multiplying 40 by the fractions, and if I ever get less than 1, all the remaining fractions are also less than 1. So I spent a little bit of time to think if that was plausible, and 40 times 1/2 is 20, 20 times 3/4 is 15, 15 times 5/6, let's see, the 3's canceled, and I'm left with 25 over 2, 25 over 2 times 7/8. This doesn't reduce very well at all. It is 175 over 16. 175 over 16. Well, I recognize that 176 is 11 times 16, so this is less than 11. How much farther do I want to go with this? So the product is definitely less than 11 times all the fractions after this point. So 11 times 9 over 10, that's 99 over 10. Well, all right, again, at least that's less than 10. So now I have an estimate of an estimate, and the whole product is less than 10 times all the remaining terms. So the next one is 11 over 12. Best I can do here is 55 over 6, I guess. Okay, so I could keep doing this a little bit more. If I'm really fast at arithmetic, I might be tempted to do this for a while, but this is not a good strategy to solve the problem. You'd have to go well into the thousands before you got this leading term to be less than 1. That's something you can check by, I guess, computer-aided computation after you're done. So, okay, one idea doesn't work out so well. So the next idea we want to do is to try and rearrange this expression into something more useful. Whenever you have a product of a bunch of terms, you're thinking factorial. Factorial doesn't have all evens or all odds, but pretty good way to deal with that. Let's look at the denominator first. So factor out all the 2's. There's 1,004 terms, so the expression in the middle, in the denominator, is 1,004 factors of 2 times 1,004 factorial. Okay, and the thing in the top is 2007 factorial, but I've divided out all of the even terms. So all of the even terms, 2, 4, 6, 8, stopping at 2006. By the same token, it's going to be 2 to the 1003 times 1003 factorial. So simplify the fraction, it's 2007 factorial over 2 to the 2007 times 1003 factorial times 1004 factorial. And when you see an expression like this with factorials of numbers that add up to the number in the numerator, this looks like a combinations, right? So this is exactly 1 over 2 to the 2007 times 2007 choose 1003. Now I thought about what this number represents, and from a probability perspective, this is the probability of flipping 1003 heads out of 2007 flips. And I thought that thinking about it in this kind of an application might help us out a little bit. One way it does help us is it gives us a second proof for the first inequality. If you flip 2007 coins, or one coin 2007 times, there's 2008 possibilities. You can get 0 heads, 1 head, 2 heads, all the way up to 2007 total heads. Well, among those, certainly it's more likely to get 1003 heads than it is than any of those random outcomes. So yeah, it kind of independently verifies this inequality. But it's harder to think about how it helps us with this inequality unless you're really good at statistics. If you are really good at statistics, you can use this idea and try to use a normal approximation to the binomial distribution, and you can get an estimate for this probability, which is pretty accurate, which hopefully is less than 1 over 40. And that might be one way to do this problem. Hard to do that without a calculator or a z-score chart, but anyway, it's something to think about. Another thing to think about is it simplifies the question a little bit if you realize that if I multiply by 2008 on the top and by 2 times 1004 on the bottom, I get a slightly more symmetric form because I can get 2008 factorial over 2 to the 2008 times 1004 factorial quantity squared. This will be useful a little bit later. So if I want to estimate a number that uses factorials, one thing that's very useful is Stirling's approximation. So this is Stirling's approximation for the factorial. If you haven't seen it before, yeah, it's useful for this kind of problem. I guess we're allowed to use it here, although now it's an approximation, so it's going to be hard to say that we've proved it unless we also have a formula for how close this approximation is to the real value. I don't have that handy. But anyway, let's see what happens if we try and use it to simplify this expression. If I plug in Stirling's formula for these factorials, I'm going to get square root of 2 pi times 2008 times 2008 over e to the 2008 power. Looks terrible, but have a little faith. Divided by, I've still got this term here, 2 to the 2008. And now I've got Stirling's approximation here. I'll write down the n over e term first. So I'm going to have 1004 over e to the 1004 power, but it's squared, so to the 2008 power. And then I've got this square root term squared, so times 2 pi times 1004. Okay, and now notice how well this thing simplifies. I've got 2 to the 2008 power, 1004 to the 2008 power, so multiply them together, and it's 2008 to the 2008 power, and it perfectly cancels out with the term in the numerator. My e's also cancel out, so all of these guys divide out to 1, and we're in pretty good shape. After that, yeah, I've got, again, I can combine this 2 with this 1004, and I could factor out the square root of pi over 2008. So the whole thing is going to be square root of 2 over square root of pi times 2008. I'm looking for an answer in the form 1 over something, so let me algebraically simplify this a little bit. It's going to be pi times 1004. Okay, so somewhat crude estimate, it's the square root of 3,000, square root of a number a little bit bigger than 3,000, and now well, anyway, 40 squared is 1,600, so this number is definitely less than 1 over 40. Again, it's not a proof that it's less than 40 because I used an approximation. So if my approximation was poor enough, then just because the approximation is less than 1 over 40, yeah, you get the point. But it's the best I could come up with, and there's still 2 more problems to go. I only have 100 minutes, so let's move on.